Okay, let me share my screen. Okay, so I'll get started for today. We are, as always, on Rockefeller. Oh, wish I could show it. RockefellerUniversity.github.io. We have our videos, and I've tried to keep up with the videos online. I think I'm still missing one of the plotting. I will add that. And we're working through our courses. We have Intro to R, plotting to R, a little bit of reproducible R in terms of the R Markdown. And then in our last sessions, we covered genomics data, the type of data we will see during our high throughput sequencing analysis. And hopefully we saw a little bit how we can, once we have processed data, data with genomic coordinates, start to be able to visualize this in a nice linear genome browser. And that's actually really useful. Whatever data you get, do try and visualize it in IGV. You'll see artifacts, you'll see features you won't discover like programmatically. Right. So the next thing we're going to cover is Bioconductor. Okay, so Bioconductor is a set of packages kind of organized by this collaboration, I guess we'll say. It really is essential for the work we do. They have built mostly based around expression arrays, a whole ecosystem of libraries which are interoperable and very easy to follow. So let's have a little talk through these first few slides. I'm just going to introduce us to Bioconductor, and then I got one other session I want to run in this first part. So Bioconductor is an open source, which is very important. We can see every bit of code in Bioconductor, community driven, so it's not. There are a core team, but really it's people like you and me writing their packages, using their packages, writing software guides, how we can use them. Started in 2001 with one of the R's from R, right? Robert Gentleman. He's more of a biologist, I guess, computational biologist than Ross or Harker. And it's gained popularity, as I say, through microarray analysis. So when I first started analyzing data, this is where I came across Bioconductor. And actually, I was using a lot of this package now, Murray, but also Lima. This has been around for over 20 years, Lima, and it's still used for RNA-seq analysis now. Okay, so it's a very robust, tested package. Importantly, all the packages in Bioconductor are reviewed. We're not talking necessarily analytical quality, so the algorithms in them, but they are reviewed to make sure they work, and that any user can download them, and they have reasonable guide explanation of how it should be used. All packages are versioned as well, which is important for when you come back to rerun your code. You want to make sure you're using the same version. It's made slightly trickier that Bioconductor has two major releases every year. Two major releases every year. So they will have, and I will show you this, a 3.11 release, a 3.12 release. This just means all their packages will be tested, checked, and updated every 6 months. R, on the other hand, used to do this every 6 months, but now does it every year. So you can get a new version of R every year, but you can get a new set of Bioconductor libraries twice a year. Why we're going to be using Bioconductor is because it has great support for high throughput sequencing. And like I was saying, it's really the interoperability between these packages. One package will build on another, so we learn the functionality in that package and we can use it while taking advantage of other packages. So the broad goal of Bioconductor was provide widespread access to powerful statistical and graphical tools for the analysis of genomics data. That's changed now because they're doing more imaging data, but really to build this broad range of tools. Facilitate the inclusion of biological metadata in the analysis of genomics data, and that's things like publications. We can query PubMed IDs, but more importantly, perhaps, we can get annotation for our genes and functions straight from Bioconductor. Common software package to enable rapid development, deployment of your own tools. And as I'll show you, they have a really great way if you want to develop your own tools. It's actually a lot of fun, and they make it very easy. The thing which they do very well is provide high quality documentation, and this is really what separates Bioconductor from CRAN, which has great documentation, but they're missing a real key component we'll show you. And the final part of their goal is to provide training. Okay. So as I'm giving a class here, you'll also find lots of little pieces of training on particular elements of analysis on the Bioconductor website. So this is Bioconductor. Let me take you to the page. Okay, here we go. This is Bioconductor. You can see the homepage and various information here on their conferences, but importantly, information on how to install, how to learn to use, how to use it, courses, educational material, including some of our material is up here when we've been to Bioconductor, and then tools for people who want to develop their own software. Now, we're not going to cover any development software here, but if you wanted to, have a look here, and we're happy to discuss. So Bioconductor is broadly split into 4 groups. We have software tools. These are things which we use to analyze our data. We have annotation data, and this is things like gene to other or symbol to different ID mappings, symbol to functions. In fact, as we'll see in our second session today, they have whole genome sequences pre-compiled and built into packages of work. You also get experimental data, which is really useful. Both, it's good that you can actually integrate some of this data with your own work, but it means you have real data to pick up and test with these packages, which is fantastic. They also have workflows, which we're not going to cover here, but they will have descriptions of how to go from one part of the data to another. So I think that's not true. We're no longer currently on 3.14. We are on now 3.15. So like I was saying, there are releases every 6 months. If you ever wanted to go back and get an old version, you can just come to Bioconductor and install an old version. It takes around 2,000 software packages. I'm not sure how to easily check that. But all these packages have been reviewed. So they have been submitted to something which has changed over the years, but a system where Bioconductor core members will come in, check your package. It's tested and evaluated automatically. That's very important. It means that any other changes which your package may depend on, Bioconductor has this testing system, which I may show in a few slides. And also they are actively maintained. So Bioconductor, we have around 6 packages now, I think, in Bioconductor. And I can tell you, they email you, they hassle you if there's a problem, and make sure you're taking care of your package. So any packages which are submitted to Bioconductor need to pass some guidelines. These include manual and examples, and all these need to work out of the box within 10 minutes or something. And they check your code integrity. So they just make sure that you're not writing awful code which isn't going to fall apart in future versions. We can have a little look at their website here. So this is how you submit a package to Bioconductor, and we can see right now there are 32 packages being reviewed. If you ever wanted to spy on other people's older reviews, you can have a look. We have Herpa, we're going to use that in a bit. There we have Herpa. And you can see it's like an open conversation, and anyone can chime in when we're being reviewed. So if anyone wants to look at the package, it's very open. But usually it bounces back and forth until we fix all the problems, fix all the both philosophical sometimes and computational, and then that will be submitted to the test systems, which look like this, and you can see every package is evaluated automatically. So you're never going to get a shock. This package I just downloaded doesn't work because it is automatically assessed. So they can all be built in the latest version of R. Examples, so when we do question mark in a function, we saw there was an example, that is automatically evaluated to make sure it works. And really important, this is something which CRAN doesn't do, is we have vignettes. And the vignette needs to compile and work. So let's have a little look. This is one of our really old packages. Base call QC. If we look at this front page here, you can see every package has a title, description, has a citation, has the installation instructions such that you can just copy and paste. And I'm going to talk about this in a second. But really importantly, they all have a vignette. So we have reference manuals. We've seen these before, and these just contain what we would do if we do question mark. So they contain like the example, the value, the description. But a vignette is so much better. The vignette is actually kind of talks you through the usage of the package. So it's not just this function does this. It is kind of a workflow. You start here. This is how we intend you to use the package. You can make these as neat or as ugly or as short as you want them to be. But that's where the reviewer will come in and say, your vignette's not good enough. You need to describe this better. Installing packages is quite straightforward. So we know that CRAN, we could just do install.packages. And it will go install our package. We can't quite do that here, right? Because actually it's a different repository holding the packages. So CRAN holds most of the common packages. Bioconductor is this repository which holds all our packages to do with bioinformatics, really. So we need to install a package to install Bioconductor packages. Okay, and that package is BioC Manager. And BioC Manager, the only function we're ever really going to use is install. And in this case, this is exactly what you would copy off their website. So really, if you're ever going to install a package from Bioconductor, you just go to their website, copy and paste this, and put it into your R session. Okay. Make sure you have all the dependencies and make sure you have the package itself. There is the possibility, if you want, you can actually check what version you're on in Bioconductor. Like, remember, we have release every 6 months. You can check what your current version is by setting BioManager version. It will tell you the version. If you really want to update to a particular version of Bioconductor, you can do BioC Manager install and just tell it the version you want to try and move to. Word of caution here. Once you've started working on a project, I don't recommend updating your versions of Bioconductor or your R. You can have multiple versions of R on your computer. I recommend installing a new version of R, installing new packages there. Because otherwise you might find yourself in a situation where a package is updated, some of the information in it has now changed, and your result usually is oh so subtly different. That will upset you, and it will be a pain. You lose one gene, you have to remake a figure or something. Once you've started installing packages, stay in the version you are. If you want a new set, install a new R, and I can help you set that up if you're on Mac. Windows is very straightforward. We have that reference manual I briefly showed. This contains details of the function's input. It is the same as if it's the same as if I do question mark kind of function. So when I do this, it gives me the name of the function, the description, the usage, the arguments, and all this, and an example at the end. When we come to these reference manuals, it's just a compilation of every single function. Right, so it's all the help pages for every function in a package put into one place. So that can be useful if you just want to see what's available for a package. Again, it's this vignette, which is really useful. So every package needs to have at least one vignette. You will find some of the bigger packages, really used, well-used packages, will often have a fake vignette. So they will have a vignette which is one line that will say, please go to my website. There they will have a full book. Bioconductor keeps very careful control over that. So they let some people get away with it as long as they have proof of maintaining other sources of information online. And one of the ones we'll see is Cluster Profiler. Maybe I can just show you that. They're a very popular package. I think if we go to the thing, has very little information on this page. It just tells us to go to his book. But once we get to his book, we've got 4 days worth of read. So the real reason we're kind of trying to use Bioconductor is because we want to start to handle biological data in terms of genomics data. And this is what Bioconductor is really built for. So we're going to be focusing on high throughput sequencing. Not much of what you're going to learn you can apply to any genomics data. So that means we're hoping Bioconductor has methods for handling our common genomics data types faster, FastQ. So that's usually our reference genome, our sequence data, our bed files, our bed 6, our narrow peak, our broad peak, our GFF, this is our gene models, and our aligned data, SAM and BAM. We have just that. Genomics data is stored as FASTA files. We have the biostrings package. This is what we're going to see this morning. Just handle data, read them FASTAs, treat them like lists. We have genomics data, sorry, genomic interval, which is bed files, and a lot of information is stored like this: chromosome start end, metadata associated with that particular region. We can handle that with both the R-track layer for import, output, and the genomic ranges, because we can consider each one of these lines a range. We've got a whole package to deal with that. Again, our track layer G ranges is going to allow us to handle and make our bigwigs. For GFFs, we've got the genomic features package. For FastQ, we're going to use the short read package. For SAM and BAM, we can use the genomic alignments package, which is really fantastic. And then on top of having software to deal with the different types of data, we're also going to have annotation packages, which are going to contain things like gene to ID mappings, functional annotation, gene ontology, genome sequence information, so the full genome for a human species or whatever, and then these gene and transcript models. So this is how exons are pulled together into genes. Gene annotation we're going to find in these org.db packages. So it will be org.species.idtype.db. So then for the human, it's org.hs, Homo sapiens. EG is actually Entree's gene ID. So this is the NCBI gene ID, and then DB. So we're going to have pretty much one for every model organism. And if there's an organism out there which someone's working on and they like Bioconductor, they may have added it themselves. Genomic sequencer packages are very similar. BS genome packages, they're called, and they're set up to be species, source, and the major version. So for human, here is HG19. Right, so remember, we have HG19. Major revisions of the genome, we had HG18, we have HG20, HG39 now. So this is BS genome, H sapiens, HG19 is the major revision, and the source is from the UCSC table browser. So this is another place where, like IGB, it stores some information, and that's where Bioconductor has pulled the sequence from. The models are in packages called TXDB, so transcript, database packages, species, source, major version, and then additionally a table. So in this case, it's TXDB, H sapiens, UCSC, HG19, known gene table. So I'm actually going to show you that, I think. So, oh, UCSC doesn't just take me to the browser, it is actually a university. What? Is there a Facebook page? What? Yeah, let's try that again. It's nice. The Google chose that as the top here rather than there. So here we have something called Table Browser. And again, I'm not expecting you to do this. I'm just showing you because this is really what they've done. So human, let's go back in time to HD19. We have HD19, UCSC genes, and you can see here we've got this column table, and it says known gene. There are other tables to pull from of annotation from UCSC genes, but we're going to pull known genes. So when we see this page here, and it says table, we can actually know it's taken it from that known gene table on UCSC. So this bit here. So when it says TXDB H. sapiens UCSC HG19 known gene, it's just someone's programmatically downloaded it from here. HG19 UCSC known gene. But actually, when we load these packages, it's actually going to tell us where it got it as well. Okay, so we're not going to do this exercise because I think all I'm going to ask you to do is install a package. Yeah. And again, just to remind us, to install a package in Bioconductor, we just basically go to the page itself. Just go to Facebook. We just go to this installation section and you can just copy and paste that. If there isn't a newer version, the R won't let you install. It'll just say you're on the latest version. Okay. I'm going to quickly plug myself in. Great. So that's just an introduction to the packages we're going to start talking about as we go. So the rest of this session for Bioconductor is fairly long, and we're going to try and move through it kind of quickly. In here, you're going to learn like how to handle these essential data types. So if you're not doing RNA-seq, ChIP-seq, ATAC-seq, single cell, but you are handling bound files and FASTQs, etc., these are really important sections. For those of you, who are, or you're all going to be learning RNA-seq, single cell, ChIP-seq here, but we're going to build on these tools. So I'm only going to show you what we really need to know, but everything we see, we're going to build up on as we move through these slides. So the first thing we want to cover is one of the most basic things, which is FASTA files. Okay? So how do we handle sequence information, loading, importing FASTA files into R? How can we handle them? But also, how do we actually get these from these annotation databases, these pre-built H238, H219 databases? A nice advantage of using these BS Genome packages is they're version controlled super easily, same way software is. So you're not just downloading a FASTA, saving it on your computer. You have a very easy way of knowing where you got it from, the version. The nice thing, really nice thing about BS Genome is it's so interoperable. So your one package will use the BS Genome, another will. It's so much easier to work with. So we saw what a reference genome looked like in our first sessions. Collection of contigs. We have a start line here with a greater than symbol. We have information on the actual chromosome name. And then we have a stretch of sequence, and this will go on for millions of lines, thousands of lines, covering all the information from chromosome, say, 1, and then we'll have another header line, and then it will say chromosome 2, all the sequence information. So we know it's stored in FASTA format. Genomic sequences can be handled in Bioconductor using this bio strings format. And the full genome should be available to us using these BS genome packages. Actually, I haven't really checked that. Let's see how many BS genome packages we have. So all these BS genome packages here. In fact, if we wanted to go install annotation somewhere, we would have BS genome here. You can see we do have a ton. 112 full genomes held in Bioconductor. Mouse, rat, Drosophila, all the common will be there. So to load a BS genome package, once we've installed it, we just need to use our usual library. And we can load the package. And we'll load the package into R for us, all the functions. Importantly, when we load the package, it also loads an object for us. So it puts an object into our environment. And that object is called the name of the package. Okay. So if we take class, if we check what type of object is that, so far we've seen lists, data frames, matrices. In this case, we got something new, a BS genome object. Okay. So we don't know what to do with this object yet. If we just type this object into R and press enter, it has a special print method, so it's going to show us some information about the object. So hopefully this is already useful. It tells us the provider, UCSC, we know that through this. It tells us the version, genome, M10, it tells us the full species, it tells us the release date. This is over 10 years old, the sequence. There is MM39 now. It tells us how many sequences it has. And those include chromosome 1, 2, the standard chromosomes. Right? But then we see some things perhaps we don't really recognize, chromosome GL, whatever. These are unplaced contents. Again, I think we talked about this briefly in the FASTA thing, but not all the genome, even at this point with NM10, they don't know where all the pieces of the sequences go together. Right? So karyotyping doesn't quite help them here, probably because it's maybe repetitive, could be on 2 genomes. So we know they exist, but we don't know whereabouts in the genome to put them. So we often ignore these, but we might want to include them for alignment, depending on how many of these there are already. But these are our major chromosomes, and these are our unplaced contents. We also see something at the bottom which looks really useful. It tells us some instructions on what to do. We can use the seq names packet function on our object to see all the sequence names. So at the moment we know there are 66, we can't see them. So dot, telling us they're only showing us a subset. And we can see here we can use $ or double square brackets, just like we did with lists, to extract the particular sequence for, in this case, a given chromosome. So there we go. Simply by doing the object, it gave us some information. Seq names will give us contig names, and we can access the actual contig sequence by doing $ and the name of the contig, or double square brackets, the name of it. So just like lists. So let's do our first one. We'll do seq names, and we'll do this on the BS genome object. I'm just going to show you the first 22 because then it goes into the chromosome ums. But if we do seq names and we get this, we just get a vector, character vector, with all our seq names ordered in a reasonably sensible way here. It's chromosome 19, and then the 2 sex chromosomes, and then chromosome 8. Any questions? We can also use this function seq lengths. So seq lengths is very useful because it's going to give us the total length of the contigs which we're looking at. So in this case, if I do seq lengths and the object, it gives me back here, just looking at the first 4, a named numeric vector. So this is the actual vector here, and these are the names for every element in our vector. So obviously they're ordered by the size of chromosomes from chromosome 1. So chromosome 1 is very big, chromosome 2, chromosome 3, 4. If we actually want to get into the object and start to pull out some sequence data, which is going to be what's most useful to us, we can just use these two accessors we saw with lists, where we can do $. Given I know all the chromosome names now from seq names, I can just do $chromosome 19. And if I put that to another object, you can see I can then print it and I get something new, a DNA string. So this is now from the biostrings library. We have a special object, which is a DNA string object. Looks a lot like it's going to be a vector of characters. Right? We've got strings here of the first bases in the genome and the end bases of the genome. And we know how long it is. It is a bit frustrating that I show this and it's all ends. It just happens to be the beginning and the end of chromosomes aren't very well sequenced. We're not exactly sure what they're there. I think with the Pan Genome Project, we're getting a much better idea. Again, we can also use our other accessor. So while here we're doing $chromosome 19, we can actually do it with double square brackets. This is a little easier if we want to do this programmatically. You might want to loop through the length of the chromosomes and then extract based on a name the sequence for a chromosome. But it still gives us the same object here. If we look at this, like I was saying, we have a new object. We can use class again. Have a little look at this object. And it's a DNA string object from the biostrings package. We don't need to know anything more than that. It's just a new type of object we're handling. The really important thing about DNA string objects is that they handle memory way better than a character. So this is a long, I don't even know how to translate that into 61 million long DNA character, right? That's going to be hard to access. It's taking up a lot of memory in R. So DNA string sets are efficiently written with a little bit of C++ and allow us to access it well, or quickly, efficiently. It's just so much better than handling this object in base R. If you want to know a little bit about more DNA string objects, you can always just do our question mark. Oh, I did double question mark, sorry. So double question mark just searches all of our single question mark. And we can see we have some information, including some examples on how to build our own DNA string, and some examples on other tools and tricks we can use with it. Probably one of the first things we're going to do is extract a sequence over a region of interest. And even though these look a little strange, they actually can be handled just like a standard character vector. So if we want to access a particular part of the string, we know in this long sequence exactly where to look. Here, I can just use standard square bracket indexing. I can say I want the sequence from 1 to whatever this is, 10 million. And then I get a sub DNA string object to return to me a smaller DNA string object of just the area which I requested here by indexing, 1 to 10 million. As I said, DNA string is a special type of object. It's written to be faster than standard character vectors. So if you want to do this very efficiently, low memory, you should actually use this function Subseq. So Subseq, as it says, is a much faster implementation of subsetting for DNA string objects. We just need to give it the DNA string object. We need to tell it where we want to extract a sequence from, start of the sequence, and then the end of the sequence. And it's going to do the same as if we just did standard indexing, but it's going to do it a lot more efficiently. You're not going to notice that you do it once. But if you start to do this in a loop, you want to pull out 100 sequences, 1,000 sequences, you will start to notice the differences. So like a very common thing we do, extract sequences under where we believe a transcription factor is bound, and then we look for a motif, a particular pattern. We will be using this Subseq function when we get it. A very useful thing we can do with efficiently using these biostring objects is alphabet frequency. So given a long DNA string, it can just give us the frequency of A, C, G, and T. You can also get the N. Right? So we know that there was a lot of N's. You can see them at the beginning and the end of the chromosome. Yeah. In this case, we can just use alphabet frequency. We can give it the full chromosome, and very efficiently, it's going to return us in a fraction of a second the total A, C, G, or T. Again, this is going to be very useful when we start to worry about biases. Is our sequences GT rich? This may cause a problem in sequencing, and that's what we want to know from these things like alphabet frequency. We can also do some really simple things, which I think are often useful to people. If we want to take our sequence and find the complement, and that's, A is a T, G is a C, we can just run the complement function on any length of string, no matter how long it was, and we will get a DNA string, which is the complement. Similarly, we can do reverse, and we can just reverse the string very efficiently, and we can do reverse complement, which is the other strand working the other way. So we can do complement, reverse, reverse complement. We can do this on substrings. Hopefully we can see here we actually did get the reverse complement. You may want to actually translate your sequence as well. You may want to know whether or not, given the sequence for a gene, you want to know when the methionine, when the start codon is. You can do that with this function translate. You just need to give it a sequence. And here I'm just giving it enough of a sequence, 9, 3 per codon. So we should just get a 3-letter amino acid back. And if I do translate on my 9 base pairs of sequence, it gives me back something very similar to what we had. Up to this point, we've had a DNA string object. Now I have an AA string object. It's just an amino acid string object. The only difference between an AA string object and a DNA string object is the allowed bases. We also have a few, just let me skip ahead to see what we've got coming. Okay, so these two functions here, count pattern and match pattern, are again incredibly efficient. They're going to work really fast on these DNA string objects. Count pattern and match pattern are very useful if you have a pretty set pattern. If you're going to be looking for more complex regular expressions, PWMs, if you know what that is, we're going to be looking at that later. And that's probably more useful for motif hunting. But if you want to find a simple pattern, let's say a tartar box at the beginning of a gene, right, we can use count pattern very efficiently. We just need to provide the DNA string we want to search over, and we give it the pattern which we want to try and find in that string. Okay, so count pattern will just give us the number of times it finds that pattern. We can have slight more control over that. We might want to be able to accept, okay, I'm going to allow anywhere between 0 and 2 mismatches from my pattern, and that's acceptable for me to still count it. I just need to use the max mismatch parameter and say I'm willing to accept 2, and the min match mismatch parameter. Here we set 0. You can see clearly I'll get a lot more counts if I'm a little bit less conservative with my matching. If you have an understanding of IUPAC code, which I really don't, but if you do have an understanding of IUPAC code, you can also use that and in some way get a regular expression search. So we have our standard ACGT, but we can also use M, which means it could be an A or a C. We could use R, which could mean it's an A or a G, W, etc., etc., etc. N, we already know, it could be any of them. So we can use this IUPAC code map too. We just need to set this argument fixed equals false. And now it will recognize things like R to be an A or G. And when we do our search, again, we're going to have a lot more found counts because we just made a much more relaxed here matching pattern. Typically, when you want to scan, you want to find how many times do I find this in a particular genome or a sequence. You want to do both the main strand and the reverse complement strand. Okay? And then we really want to get a count of the chromosome. We'll do standard, reverse complement, and we'll sum them together. So already, with our kind of knowledge, we can do something useful. We can give it our pattern, we can give it our subject, and then I'm going to give it reverse complement of the object, the chromosome 918 object, and it's going to get a scan of both positive and negative strand. We could also just reverse complement that, search for a different strand, and we just add them together, and this will give us our total counts for this sequence across the chromosome 19. And I really encourage you just to follow along and have a go at that, because you'll see just how fast this is. Okay. So as with everything, I'm going to show you like there are biostring objects for these things, right? But a lot of you will have in your lab a FASTA file which is used for your analysis. So we still want to take advantage of biostring objects because then we have these things like Subseq, which are super fast ways of getting data out of them, count. But the reality is you're not often going to be able to just accept, I will use this reference for my project while the rest of my lab uses another reference. It's just not practical. So there are ways to create whole biostring packages yourselves, but often you just don't need to. You just need to be able to create a DNA string set which contains your chromosomes. The first thing we'll do is write out our FASTA. That could be a way around. I might want to say, how about I share my reference with you? To write out our FASTA, we need to change our DNA string into what is basically a DNA string list, except it's called DNA string set. Okay, so we just provide here DNA string set, and we give it just a little DNA string. Then we have this DNA string set. I need to assign names to it. So if I provided multiple, separated by comma here, multiple sequences, I want to assign a name to each sequence. And here I'm going to assign it chromosome 19. And then I can just do write X string set, chromosome 19 seq set. I'm going to have to give it a file path here. And I can tell it to go write this out. Importantly, if I say .fa, it knows to write out a FASTA file. Right? So I'm not saying format to write out here. By saying write X string set, giving it my DNA string list with a name, it just checks what my extension is, and it's going to write out a FASTA file. So let me see if I actually have that FASTA file. I can probably get it. Let me see if I'm home. Don't have that FASTA file, but I have another. Okay. Let me move this up a bit. We have the object, we have all the chromosome names. Let's take a bit of one chromosome. Okay. And I can subset that. Let's do it standard. Let's do Subseq. And then start equals 10. 10 equals 20. Okay. Right. So that gives me a DNA string. And I can turn that into a DNA string set. I don't have any names in temp, so I'll give it a name. So now I have my DNA string set, width 11, sequence there, and I have a name for it. I should then be able to do write X string set, give it my object, file path is, hopefully in my present working directory, should have template. It's not a very interesting FASTA file, but it has everything we want. The names now got put there in the ID thing, right? So this is a valid FASTA file. And then you could actually read this back into R, or you could then, if you were, say, writing out your full genome, you could then pass that to Go Collaborate and say, this is what I use for my life. So as I just said, we can then also then read it back in. So if we do read DNA string set, this allows us to read a FASTA file on our local computer. Just need to say the file path. And then once I have that, I have my DNA string set. I can do the same things as I had to do to get sequences from my biostrings object earlier on, my PSUM object. And you can use $ and give it the chromosome name, or I can use the double square brackets and put the quote chromosome name. So that's the end of the first session for today. A little early. I have some exercises here on working with this. It shouldn't be too complex, but let me know. We don't have a TA today, he's ill. So wish him best. So if you have any questions, please hold on. I need to have a meeting at 2, but I will be around and just raise them or put them or email me and I will try and test them as quickly. Okay, so after the break, we'll probably just run through these quickly. But we have a really cool session. It's one of my favorite sessions, which is it Genomic Ranges. So I recommend hanging around for that. It is a long session, but really useful. I think this is the next session there. While we're showing you how to deal with sequences, this is going to show you how to deal with ranges. And that's a lot of genomics is about. Okay, I'm going to load back up those exercises. I'll be back, be around, but I'll be back short. 2:30. If you want to go and catch up the rest of it on Zoom, we're always on Zoom. All the videos will be on YouTube, hopefully by the end of the day. Ah, David is around. He's on. So David's on Zoom, it's not physically in. Final thing I forgot to mention. There will not be a class on Monday. Sorry, I can't make it on Monday. Personally, I won't be here on Monday. We are ahead, so we're doing well anyway. I am always available by email. I'm going to send an email as well. Okay, so I'm going to hop into the next session and I will come to the exercises at the end of today. So a little longer. So I will do the exercises for the first session and this session now at the end of the day. Okay, so we are resuming our introduction to Bioconductor. We're just moving down to the next session, which is this introduction to the Genomic Ranges package, manipulating genomic intervals, import, export of their files. So yeah, I mean, this is, as I said, I'm always very excited about the Genomic Ranges package. Back when I first started doing high throughput sequencing analysis, these tool sets weren't available. So people were coding their own tool sets, often with slight bugs. A really famous tool set for doing this, and I'm not sure if anyone knows it, slightly strange name, is bed tools. Tools for operating with bed files. So there is a whole set of tools using that, and that's a shell-based to just run it on the command line. For me, Genomic Ranges is pretty life-changing in terms of the analysis we can now do with it. So here we have Really, how we represent genomic intervals is files. We just use a bed file. Okay, so the simplest bed file we can see or use is just 3 tab-separated columns. Start a chromosome. So we have the chromosome name, tab-separated start, tab-separated end. And this would be a interval, this first region here. So it's also a genomic interval because it's got a chromosome. So we know something happened or something of interest on this chromosome within this region. And that's really an interesting concept we're going to have to start coming across, is the idea of a range. Right? This isn't just one number and a second number, it's the data in between, the space in between. So in genomics and high-throughput sequencing, we're going to make extensive use of genomic intervals, and with just those, you can already make some really nice discoveries. We use it to store simple annotation, summarized results over regions. Often, we don't need the complexity of a BAM file or a bigwig, where we can see signal base pair resolution. We just need to know this much signal over my gene. This is how well expressed it is. Maybe we just need to know where the transcriptional start site is, where its nearest enhancer element, the element to control gene expression is. And I started in epigenetics. So summarizing signal from ChIP-seq, I have this much of an active mark like we saw in IGV over a gene. I could represent that as a bed file, chromosome start, end of the gene, maybe the name of the gene, the strand, and the score would be the summarized signal. So often we're going to reduce things down to just a range, and we will then work with that. We also want to assess, now we have a linear genome, spatial relationships between such genomic intervals. And that can be things like transcriptional start sites and their nearest enhancer, the distance, or maybe just any distance. We just want to find the nearest. This is an operation we can perform using genomic ranges. And just overlapping, say, our region of signal with known transcriptional start sites. That's a one-line thing in genomic ranges. But it's very powerful and important for us to be able to do it. So to get started with genomic intervals in Bioconductor, we can first make or be aware of the 2 packages which are going to allow us to do this. And that is the Genomic Ranges package, which has all the operations we need to be able to handle these genomic intervals. So that's create new genomic intervals, overlap genomic intervals, find the nearest. All that's going to be in genomic ranges. Our track layer is our kind of I/O tool, it's the input-output tool for these types of genomic data. So our track layer, I'm not sure if there is actually a track layer software, but this is going to handle import, output, export of genomic intervals, not just bed files, but we'll see later, bigwigs, BAM files can all be read in using our track. So this is our I/O for genomics data. And in terms of intervals, Genomic Ranges is what has the software, the tools we need. So remembering, if we want to get a particular version, we can do Bioconductor install version. If you want to just install Genomic Ranges now, you can just follow this line. If you already have BioC Manager, or you can probably just Google Genomic Ranges, onto this page, and it will have an install thing here. So we can just copy and paste this. Doesn't matter if we've already installed BioC Manager, it checks for us this little line if it's installed, or we can load it, install it, and then install the package. All right. That's interesting. So I was talking about build tests earlier on. So everything being evaluated and tested. You can see here, build error. Genomic Ranges is failing. So there's a new version someone's trying to create probably and put some new features in, and it's broken. That's great, because actually it means that we here, this version we've got, these will be active and working, but until this build passes, we won't get the new version available to us. I'm sure someone in Bioconductor is going to alert and picking that up. Once we have any package, we can load it, library, and we have all the functionality available to us. And we can start to create some ranges. So the first thing we need to do with Genomic Ranges object is create a set of genomic intervals. Intervals, genomic or non-genomic, are created using a sub-package called iRanges, so interval ranges, whereas G-ranges are genomic. iRanges, if you're not doing any genomics, are actually super useful because they allow you to find regions which overlap between ranges. We actually use them when we build these slides to make sure we don't if we have two code chunks we want to present to you, we want to make sure that we don't have certain words within them. We can check that using these iRanges, just as start and end positions. So if we want to create an iRanges, we just use this iRanges function. And we just need to provide two arguments. We need to give start positions, and we need to get end positions. So here I'm providing 3 start positions and 3 end positions. So we're going to have a start at 1, which ends at 2, start at 10, ends at 11, start at 20, which ends at 30. Once we've created these ranges, interval ranges, we can check our class. We can see it's an iRanges object from the iRanges package. So this is our very simple ranges. If we type this in, we can see how it's displayed, and it's giving us the information we gave it, a start and an end. Additionally, it adds another column for us, width. It's obviously just calculating that as we go. It looks a little like a data frame, but it's not quite. Something special about this. We know it's the special object. We have our ranges. We just don't have any chromosome information yet, so we couldn't use them for genomics yet. We just know on whatever they're on, starts at 1, ends at 2, starts at 10, ends at 11, 20, 3 ranges. To create a genomic ranges, we just need to add on top of those. So we need to add to this some genomics, in this case, chromosome names. What we're going to do is use this Granges function, which is from the Genomic Ranges package. We provide our intervals here, and then we provide additionally now some seq names to go with our intervals. So chromosome 1, 1, 2 to correspond to our 3 regions here. So then if I provide my iRanges there, remembering this is my iRanges, I provide additionally the seq names. And if I check the class, I no longer have an iRanges, I have a Granges, Genomic Ranges from the Genomic Ranges. So this now contains our original intervals in a slightly compressed manner. So it's kind of fitted them into this one column here. We have additionally our contigs now, we have our seq names. And actually, you can see at the top, it's telling us what each of these components are. We have an iRanges there. We have an RLE here. I'm going to explain what that is in a few slides. And it's also added a little bit of strand information. Okay, we didn't provide any strand information, so it's just by default filled them in with a star. Just like a data frame, we can retrieve rows from our genomic ranges just by doing my genomic intervals. And if I want the second and third row, I just need to provide the index. Here I'm providing a vector of 2 numbers, 2 and 3. It means it's going to extract the second and the third range. So that's like a data frame. Before the comma rows, we would hope that after the comma columns. It's not quite the case for genomic ranges. In fact, for rows, we don't actually need the comma. Right? So actually, if I say 2 or 3, it's still going to get me the second and third row. Okay? I don't need to specify the comma. It's going to allow me, it won't give me an error. If I don't specify it, I will select first, second, and third. So that leaves us with a problem. How do we get the columns? Right? Because there are column information there. I want the seq names, the ranges, the strand. We can't actually extract them in the same way we would a data frame. And that's because these are intervals now. They're not really, they look a little bit like a data frame, but they're not. Okay. If we want to access those particular columns, we need to use accessors. So these are functions which will allow us to pull and set the values within those columns. Okay, so we can use seq names, start, and end to retrieve the seq names column, the ranges column, or the strand column. Sorry, the start of the ranges or the end of the ranges. There is a function strand we'll show us. So if I want to get the start, I can just do start 1, 10, 20. It's a standard vector then, nothing special about this. If I do end on my genomic intervals, it will pull out my end regions. I can also set my regions, right? So if I now want to manually adjust my G ranges, I can just do start on these genomic regions and then assign to it some new values. So for a data frame, we would typically do $, the name of the column, and assign the values. In this case, we have to use this function start, give it the object, and we can assign new values to it. And if I then retrieve them back out using the start function, I'll get these values. Part of the reason that we can't directly access the elements within a G ranges is because it wants to do some checks for us. Right, so if we do start now and I set them to be 10, 50, and 150, we just go back to our G ranges here, we can see that the end positions are quite like 2, 11, 30. I try and set the start to be after the end, that's going to be an invalid G range. Right? You can't have a start before the end, after the end, otherwise the end is now the start. Right? So if I try and set that, it's going to tell me exactly what went wrong. The width can't be negative, it's start from the end, and it's an invalid class of G ranges. Okay, so I can access these elements of my G ranges, but I can't do it without rules. It's going to assess it for me to make sure it's still valid. Chromosome names, we can also do the same. So we can use seq names now, accessor on our G ranges intervals, our G ranges object. And then we will get back a little special type of an object, a factor RLE. We can recognize the factor part, but an RLE is something we haven't really come across yet. This is run length encoding. I'm not sure if I'm going to discuss it yet. I'll discuss it now. So run length encoding is just a way that computers can save a bit of space, right? And you can already see the example here. If I have 2 chromosome 1s in a row, I don't type out chromosome 1 twice. I type chromosome 1 and I say length 2. Right? If I had chromosome 1 a million times in a row, which you may have in an ordered bed file, writing out chromosome 1 a million times is just taking way too much space. So we can just say chromosome 1, and if it was a million times, I would say a million there. It was chromosome 2, and here we've just got 1, but I can easily save myself space. We don't need to worry about that because actually we can deal or convert those 2 characters, so they're objects we know now, by just using this as.character function. So if I get my contig names and they're this factor RLE and I'm not sure how to deal with it, I can just turn it into a character vector with as.character. Now it's something I can actually work with. It's a standard character vector. As I say, RLEs save memory. We will come back to RLEs when we actually need to use them. This is going to be in bigwigs genomics. It's actually the next session. As with start and end, we can reset our seq levels. Okay, and if anyone has actually done genomics already, we know, let's say, not everyone calls chromosome 2 chromosome 2. Ensemble call it just 2. So we do need to change these names every so often. If we want to change the seq names, though, we can just do seq names, just like with start and end. We can give it a vector, and then we will get now, I think I set here the first 2 chromosomes, chromosome 1 and 2. And here I've just reversed it. I'm calling them chromosome 2 and then 1. Already we can see that there is going to be a slight complication here. If we just look at the name of this object, it is called a factor RLE, and it has levels. So if you remember with factors and levels, if we want to replace in a factor, and we want to add something which is not in the levels, we're going to have issues. It's going to give us an NA. It's going to say this doesn't exist in our factor. So we can try that here. So it's just the same rules as standard factors. If I try and change now my first seq name to be chromosome 3, Look at this, error, normalize, whatever, levels of, I can't quite pull it off the side of the page, but levels of supplied seq names must be in previous levels. So they need to be here in order to add a new seq name. Luckily, we can fix that pretty easily. We have a special function, just like we had levels function for factors, we now have seq levels for genomic ranges. So if we want to change the sequence levels, these levels here used for the seq names, we can just do seq levels, my genomic intervals, and it will list them. So here we just have chromosome 1, chromosome 2. If I want to be able to add things from chromosome 3 here, I can do seq levels and I can assign it my new levels. And here I'm going to say chromosome 1, chromosome 2, and additionally chromosome 3, which is the value I wanted to be able to put in. 1, 2, 3. Okay, so now if I try and replace that final one with chromosome 3, you can see it didn't give me an error, just created that. Go back to this one, you can see trying that, it gave me that. So if you ever get that issue, you can use your seq levels to fix your G ranges, add the additional levels for that seq, for that content of interest. It also includes strand information with G ranges objects, and this is going to become important for when we do later manipulations. We might want to say this is the nearest feature on the same strand or on a different strand. We may consider a feature doesn't overlap another feature unless it's on the same strand. Okay, so strand's important. So we can set strand to be plus, negative, or unstranded with star. And I think we saw star in some of the bed files. Typically, ChIP-seq is strandless. It's just the technology doesn't give you a strand information, typically. So here we can create a new G ranges with pre-established strand information by doing the seq names, the intervals, and then supplying strand. Again, it needs to be either plus, minus, or star. We supply nothing in strand, it will just assume it's strandless, and it will put star, like it did here. So in this case, I'm going to put positive, negative, and star. If you saw, well, if we look at the strand information, it doesn't quite say it there, but it's going to be another factor RLE. It's going to kind of force this for us. So I can reset strand information the same way, plus, plus, negative. Here I've now changed it from plus, negative, star, plus, plus, negative. I can also review the strand information using this. But what's really important here is no matter what values you have in your strand column component, it is always going to have 3 levels. So up front, Genomic Ranges sets the strand information to be just those possible 3. Right? And that makes sense because you can only really be on a positive, negative, or unstranded. For the seq names, it has no way of pre-knowing what factors you could be coming from any genome with any content. So in this case here, now with strand, we don't need to worry about releveling. It's always going to have plus, minus, or star available as its levels. Final thing we really want to set is the idea of having names. So we have names for row names previously, we've had column names, and we've had names for vectors. In this case, we can set names for our intervals by just using the names argument, just like we did for vectors. And here I can assign peak 1, peak 2, peak 3. And then I'm going to get my genomic intervals. And I've got some names on the very left associated. Obviously, the real use of that, other than when we export them, it will maintain that name in the name column. But for now, we can use those names to do our indexing. Okay, so previously we could see if we put 1 here, it would pull out the first row. This is the second peak. So I would do square brackets 2 to pull out the second range. We can actually just index it like a vector. And we can pull out, if we know the range of interest, say their gene names, we can just use standard indexing here and put the actual name we've set. On top of intervals, the actual interval itself, which would be name, chromosome, start, end, strand. We also may want to store additional information alongside those genomic intervals, and that's going to be things like score, how many reads landed in that region, what is the closest gene to that region. Any information we want to store alongside our G ranges here, we have to use the mcols. These are actually the metadata columns. Okay. So we can build the G ranges really easy with metadata columns just by, when we create the G ranges here, I can just put in, like a data frame, 3 columns or 3 names for columns. So here score, and here comment. I don't need to tell it anything additional. Here I'm going to give a score, which is a vector and numeric. Here's a score, which is a vector of characters. And then it will create. I don't actually show the data frame. Let me show it. It creates a slightly different G ranges here where we have our chromosome start end, and then we have this demarker in the way it shows us this. It tells us we have 2 metadata columns, and we now have score and comment. And this is numeric, this is just like we supplied. So these are our original ranges, our 3 ranges here. And then we have 2 metadata columns, and you can tell because it puts a sort of like dashed line. Once we have those set up, we can actually access those columns from the metadata columns just like we would a data frame. So we can do $score or $comment. And because I have them here, score and comment, it will just go look up the values from the score column or the comment column. Look. Just like a standard data frame. This is untouchable. We can't use those accessors, but this we can use standard data frame accessors to access the metadata columns. If we want to pull out just all the metadata columns in one go, we can use the mcols function, and we can supply our G ranges, and it brings out a data frame of those columns. Notice this is called capital D, capital F, and that's because this is a bioconductor version of a data frame. We'll get this a fair bit, but it acts like a data frame that's created by Bioconductor because they think they can do a slightly better job managing what a data frame has. This saves a little bit of memory. If we want to convert that into our standard data frame, it's very straightforward. We just do as.dataframe, provide the genomic ranges, and it will turn this into a nice standard data frame, seq name, start, end, width, strand, and any of our metadata columns there. So if you just want to take your G ranges and write it to a file, creating an as data frame of it, and then you can just write it to a file, use it with other programs. So these next few slides are a little bit focused on people working with us, so feel free to ignore. We saw that when we do IGV, we have this idea of chromosome 1. We can specify regions of interest like this. Let me open up IGV. See if this works. Hey Siri, can you open IGV? Clever that Siri knows to turn down how loud my fan is when I'm trying to talk to it. Let's go to some more simple HG19. So here we know that if I paste in something like this, chromosome 1, and then the range I'm interested in, it will hop to that region in IGV. This is like how IGV likes to store ranges. Very fortunately, actually saw this in a talk locally here, you can actually use the granges function directly on those ranges from IGV. So if you want to create a quick range based on your window in IGV, you can just paste that character string straight in here, and it will create a G range. Really nice. You can also supply for whatever reason, multiple characters. So I might want to supply, I might have, for whatever reason, in a table, lots of positions like this. I can get multiple regions. So actually, a lot of our data we give people is in that kind of format. We give you something like chromosome start end. It just happens for convention, we tend to include a colon there. If you want to convert that, which we've given you, into something which you can then convert into a G-ranges, we just need to be able to replace that last codon with a dash. So to do that, we can use this package stringy. If anyone's using tidyverse, they'll recognize string R built on top of stringy. We just give it the range where we have this colon, and I can use this function from here, string, replace last fixed. So it's going to replace the last occurrence of something. We tell it on my range, the string, replace colon with a dash. And when I run it, it looks through it, it finds the last colon in the string, replaces it with a dash. So now that I can paste into G-ranges or IGV and operate on. Another common format you'll get from things like MemeChip is ID from the range, so the peak name, chromosome start end. We can fix that also by using the opposite of string replace last fixed. We have string replace first fixed. And maybe I need to explain regular expressions a bit more. We don't really go into this, but effectively any character star colon. So any number of characters followed by a colon. The first time it comes across that, it just removes it and replaces it with nothing. In this case, we get rid of the my ID part. We already get rid of the colon at the end to make that a dash. And now we have something we can make into a G-ranges. You only really care about that if you're getting data from it. Okay, so we know how we can build a G-ranges. We just need to build an I-ranges, we give it seq names, and we can add metadata columns. The reason we really want to work with G-ranges, and again, you're not going to build G-ranges often yourself, you're going to import from a bed file. One of the big reasons, advantages of G-ranges, and this is why I came to G-ranges, is that it has some very simple functions available to you, like a resize, where we can change the shape or the size of a range, merge or reduce, which is an interesting concept. But given two ranges, I want to create or in this case, all 5 ranges. If I want to create a non-redundant set of ranges, I kind of collapse these onto each other. And I have from the beginning of this range now to the end of that range, I have one range which represents these two. And it's just like flattening them almost. Similarly, I can do that to this one, original. I can reduce them. I take these 3 ranges and I create one long range. We're going to do this in ChipSeq. I'm going to take peaks from different samples and we're going to create a consensus peak. Shift is really useful. We can move G-ranges back or forward or along the genome a certain distance. We might want to shift them to get the promoter region, maybe. That would be upstream from the TSS, shift it 500 base pairs. Or we could do resize, which is also very useful. So if I want to take my G-ranges and I want to resize them based on the start position, right? I could take this range here and resize it based on the start, but just do 10 base pairs. So we have these special functions for manipulating our G-ranges, and it saves us having to change the start and the end and worry about, did I make them negative and all this? It's going to take care of all this for us. So I was just going to step through some of these different tools, and then we're going to look at the second really useful thing about ranges, which is overlapping different ranges. So the shift function allows us to move our G-ranges by a particular number of base pairs. So if I have my first genomic intervals here, you can see it's 1 to 2. If I just want to shift that along the genome, 10 base pairs, I just need to provide shift, give it my G-ranges, here it can be as just one, but I can give it whole tables of G ranges. And I tell it shift at 10, and it just changes the start and the end to move them along 10 base pairs. We can also have a look to see what other options we have available for us in Shift. Lots of Shift. Nicely. So you can see you've got a whole family. These are all the ones we're going to look at. Shift, resize, flank. Not many other options, just the ability to shift it. Positive values are going to move it that way. If you want to go the other way, you can do negative values and shift it to the left of the genome. I'm not sure there is a left and right to the genome. We can also use the resize function to adjust the width of our regions. So here, if I take our genomic regions 2 to 30, and I say I now want to resize it to be 20, by default, it's going to fix on the start, and it's going to go 20 base pairs up. So resize, give it my region, tell it the width. Now it's resizing it fixed on the start to go up 20. Just like I said, by default, the resize function adjusts the width of regions from the start. Right. We can control this behavior by specifying the fix parameter. So we can do start, end, or center. Center being very useful. If you have a chip-seq peak, it's typically binding right at the center. So you want to resize it around the center, get your new bed files, and often extract the sequence to find the motif. In this case, we're just going to take that third region, and we're going to do fit my genomic intervals. Here it is. And if I want to resize it now fixed on the end, the same width, rather than going from 2 to 21, it's going to resize backwards from 30 to give us a width of 20, and it will go from 11 to 40. The resize function, by default, takes into account strand information. Okay, so if I provide here resize width equals 20, fix equals start, and this is on the positive strand, like it is here, when I say start, it believes the start to be the leftmost position in the G ranges. If I then assign now using the strand function, I'm going to assign a negative to that, and I do the resize, and I tell it the same width, and I tell it the same fix, you can see it does the opposite. It's working from the backwards. This is because, typically you want to resize around the start of genes. And genes on the negative strand starts the other side. But it's worth knowing this because paying attention, you're going to resize slightly strangely. A final function for adjusting genomic ranges, which we will review, is the reduce function. This function merges. I often wonder if merge is the right word here, but we'll stick with it. I'd say flattens, really. Merges overlapping regions into a single non-redundant genomic interval. So we can create some overlapping intervals now. We will do chromosome 1, 1, chromosome 2, 1 to 2, 2 to 11, 2 to 30. So here we have our genomic intervals. There isn't much overlap. Oh, there is actually. Here there's a fair bit of overlap. Okay. So there is, oh no, but this is on another chromosome. So these two overlap. In terms of intervals, this one overlaps with these, but it's on a different chromosome, so it shouldn't overlap. All on the same strand. If I then apply reduce to this, it reduces my ranges now just to 2. And for that range here, when we had 1 to 2 and 2 to 11, they overlap on that second base pair. So it just gives me one range going from 1 to 11. Okay. So just to show you here, it's the equivalent of these two ranges. Any overlap here, it's just going to give me one range which represents both of them. We are losing information. We no longer know there were two ranges there. We'll show you later on how we can use this effectively. Effectively, it takes all these and creates our non-redundant set of intervals. Okay. So, yes. So the reduce function also takes into account strand information, and it's only going to merge regions if they're on the same strand, right? If we do star, it's going to assume that we don't know. In this case, we have previously plus, plus, plus. If I now set plus, negative, plus, these two regions which had just overlapped are now on different strands. So by default, when we run reduce my genomic intervals, it's no longer going to reduce them. Okay? It thinks they're on the, well, it knows they're on a different strand. We can control that behavior though. If we want to ignore strand information and we want to reduce them anyway, we can do reduce my genomic intervals and we can give it ignore strand equals true. And now we have our merged genomic intervals. Okay. Notice it's set now the strand to be star. So as soon as we said this ignore strand equals true, even if we had a region which was plus and was never going to get reduced, this third region, still, because we're ignoring strand, it's now given up and just given us star for the strand information. Okay. So the main reason I came to genomic ranges originally all those years ago was because genomic ranges contained some of, I think, the first methods to overlap sets of genomic ranges. Okay, so previously we've looked at in function, right, which looks a little bit like this, where we have percentage in percentage, and we can see if in one vector we find an overlap with another vector, give us trues or falses. In this case now we can use over, right, and we can use this actually to assess which G ranges overlap another set of G ranges. So first let's create two G ranges. So we have chromosome 1, 1, 125, 20, 30, 22 to 100, 27, 20, 30. So that's what they look like. And they look like they're going to overlap. This region is going to overlap with this region. So to find all the regions in genomic interval lists, my genomic intervals 1, which overlap with intervals in my genomic intervals 2, we can use this over function. This is going to return, just as when we use the in function, a logical vector specifying if regions in this, my genomic intervals 1, overlap any regions in my genomic intervals 2. So let's check this first. So we have this region here, this region here. We know that this region is going to be overlapped at least by one interval in my second set. So if I do my genomic intervals over my genomic interval 2, then it's going to give us false true, because it was the second one here which overlapped with any regions in here. Okay. False, because this doesn't overlap with any regions. Then we don't know what regions it's overlapped with, but we could use this, say, if this was our TSS sites for genes and we just wanted to know which ones overlapped our ChIP-seq mark, we just want the true or false. We don't care about it. So with that little bit of true or false, just as we did with vectors, a true, a false, or a true can be used to index. So if I actually want to pull out the region which was overlapped by something in the second interval set, I just do my genomic intervals here, and I can do that overlap operation here, which gave us the false true. So now I can use this clever kind of genomic in, effectively, this genomic way of overlapping, to subset my regions of interest from my first. A really powerful feature, and this is going to be used throughout the course, so don't worry. We've got it in the exercises, but we'll explain this again and again, is the find overlaps function. So the find overlaps is going to improve on the over function by telling us which ones in our first list, our first region set, overlapped with which ones in our second regions. So we get a little bit more than true or false. So we'll do find overlaps, and we'll give our my genomic intervals, and we'll give it the second set of genomic intervals. So this will just be two G ranges here. We're going to get yet another class of object. So I'm not sure how I'm doing for time. So, we're going to get yet another class of object, right? And this is a sorted by query hits object from the S4 vectors package. But if we just look at it, we can see it kind of makes sense. It's telling us the second one in our first group overlapped the first one in our second group. Okay. Our query, which is this, and our subject, which is this. Okay, we can check that again. Our second one here overlapped with our first one. Okay, so it gives us this hits object, and we can see that, but then we might actually want to use those in indexing. Right? Because this is going to give us the positions of the first, which overlap with the positions of the second. So if we actually want to extract those numbers directly from this table, there are a few things we can do. Query hits will give us the query hits column. Subject hits will give us the subject hits column. And although I don't say it here, you can actually just do as.dataframe on those query hits, and it will turn this into a data frame, which means you can just take out the information as you choose. So again, we can use that indexing to now say, I want to get those which are, or the first hit, my query hits, I can use query hits, give it my Granges, my hits object, and that gives me the index, which will then match the subject hits, which come from there. So I can subset my genomic intervals list through this one, and it's this, and in the second one, it will be the overlapping region. That's going to be useful for when we could then turn that into a data frame and just put them side by side. We know that they all overlap, and we can then use that in our further analysis. We're going to come back to that in the exercise. Aside from just overlapping regions, another common operation, again, can be quite computationally expensive, which we want to perform on our genomic intervals, is to find the nearest. We may also want to be able to find the nearest but before and the nearest but after. Okay. So nearest is often used for enhancer to gene relationships. We know that we want to say this enhancer regulates its closest gene. We could use something like nearest for this. So we'll just create two genomic intervals. We show them here. Chromosome 1, 10 to 25, 20 to 30. And then on chromosome 1, one which is going to be kind of close, and one which is a fair distance away, right, past there. So this one's going to come before these regions, and this one's going to be quite a lot after. If I want to apply the nearest function, I can just give the nearest my two genomic ranges I want to compare, and it's going to return the index of the intervals in the second genomic ranges nearest to those in the first genomic ranges. So is that right? It's going to give the index of the intervals in the second and nearest to those in the first. So for the first one, we have 1, 1. So the nearest to this one is this one. And then the nearest to this one is also this one. Okay. So we have our two nearest from our second interval to all the intervals in here. And we know that in this case, this is the nearest to both of them. You can again use that to index and extract in order the G ranges which are nearest to those in the other G ranges. Proceed and follow just allow us to have a bit of direction on this. Okay, so if I want to know what is the nearest before the ranges, I can use proceed. And if I want to know the nearest after the ranges, I can use follow. So in this case, but I'm not going to show the answer to proceed. But if I look at follow, the nearest regions following it, this region is this. There's no option. It's always going to be the nearest. If we look at the nearest following this one, it's going to be this one. Proceed would have been this one twice. Another useful function here is distance to nearest, which again is going to accept the same arguments as nearest and find overlaps, except this time it's actually not just going to return the intervals of the overlap, it's also going to return the distance. Okay. So a lot of the time you may want to take the nearest, but you're not going to accept anything over a certain distance. It's just improbable that it has anything to do with that closest site. So if we run this, we get another hits object, except this hits object contains a metadata column. So we have 2 hits and 1 metadata column. If I want to get access to that, I can either use mcols on my distances returned object here, and it will extract those distances. I could also, this being a metadata column, I could just do $distance, and it will extract those distances. We can access anything in the metadata columns by using the $. So most of the time, you're going to be interested in these interval overlaps, find overlaps, nearest. You're not really going to be building G-ranges yourself. Either they're going to be the result of another program, you may import them from bed files, or you can extract them from the annotation pre-built inside Bioconductor. I told you we're going to get transcript models, we're going to know where TSSs are. You may want to get them from there. One of the first or most common places you're going to get them from is from bed files, and that's because lots of software kicks out bed files. Bed files are super easy to make them in Excel. So here we're going to do library, and we're going to use this R track layer package, which I've said is our import export for genomics data. We can use the import.bed function. To be fair, I think you can just use the import function and it will guess based on the extension. But here, if we say .bed and import.bed, we're going to get a G-ranges, and it finds the seq names, the ranges, the strand. And if this was bed 6, it's going to put the name there and the score there. If you didn't have a name or you didn't have a score, it will put star again there, star again there. If we want to export our G-ranges after we've done our manipulations, which is one of the most useful things, just those ranges which overlap TSSs, maybe shifted our ranges up, we can then actually write them out just by doing export.bed, giving it our G-ranges, and then telling it the connection. It's just to be difficult. Export bed doesn't use file equals or file path. It uses connection. Okay. That's really how you can import bed files, export bed files, and manipulate G-ranges. Okay. So that's the basis of now, say, alignments will be G-ranges plus additional alignment information. Okay. Bed graphs are G-ranges plus score information. So just to show us a little bit about how these things kind of intercept, right? And this is the real cool thing about Bioconductor. All these packages can use each other. I just want to show you how we can extract the sequence under bed files using the information we learned in our first session. So we saw earlier on, we can use this Subseq function with our BS genome object. In this case, I'm doing Subseq. I'm taking a chromosome 10 from that object. I just want 1 to 100. With G-ranges objects, once we have a BS genome loaded, we can actually use this getSeq function. We give it our BS genome object, and we give it the peaks that we want to extract underneath. So we want to get the sequence under these regions. And then it returns to me in one line a DNA string set object containing the sequence under these peaks or within these ranges extracted from this BS genome object. Right, so here I'm just showing 3, but actually you could do this with your full ChIP-seq, get the sequences, and then you would pass them to your motif finding tool. In order to get them out, to pass to your motif finding tool, we just do write x string set, give it those sequences, again, tell it it's a FASTA file, And then we should be able to get a valid FASTA file containing the sequences underneath our bed file regions of interest. Okay, so that's the end of our session today. I know that's actually quite a lot to take in for one session, but I promise you we're going to do that over and over again. All these other objects are built, as you can already see, they all interact with each other. And really we're going to build, say, an alignment is a combination of a G ranges, the sequence, so a BS genome object, all wrapped up together. So we don't need to learn anything new. We're going to just expand on what we have from this. We're going to see this over and over again. So I have some exercises, and these are starting to get a little complex. Nothing we haven't covered, but using everything we know. I'm going to give an hour for these exercises, and then at 4:30, maybe 4:20, I will run through, I'll do it at 4:30 just to be consistent. I will run through our first session exercises and our the second session exercises. Again, I will put all this up on YouTube, so if you don't want to hang around for that, you can catch up. But if you want to leave now and just watch the send session on Zoom, please feel free. I will be here. Okay, so let's work through the solutions here. I'm just going to work through the solutions on the page. If I can find it, great. But feel free to interrupt me in the chat or in the room if you feel like it. So first thing first, we'll load the library. So there's this library, BS Genome, H. sapiens, UCSC, HD19. We've already installed it. That will load the library, and then we will have this object available to us, BS Genome, H. sapiens, UCSC. In the line above, and I explained this in class, I wrap this function to load the library within another function, suppress package startup messages. This just meant when I make it in an R markdown, when I load the library, it's not going to spit out messages to the console or to my report. Otherwise, and I think we saw this earlier on, if I just go into R, look. Oh, that's good. Let's try that one. You can see all those messages there got printed to my console. I can find another one I haven't loaded yet. I have already loaded. Oh well, I can just show you anyway. Suppress package startup messages. It will be absolutely silent when we run this. It just tells it to not print information to the screen, which is really important for when you want to make a report. You don't want that printed to the report. Give the sum of the length of the 3 smallest chromosomes. So we can get lengths of chromosomes using the seq lengths function. If we have a look at this, I can just run this quickly. And oh, I'm going to load that library. Oh, I don't have that. Nope. I don't think I've got this library installed yet. So I'll do it on 38 for now. It's not going to give you the same answer, but it's the same idea. So then if I do seq lengths, but now using HD38, I get the contact lengths here. I could find the smallest by ordering them. Decreasing length equals true. If I take just the order and then the first 3, it should be decreasing equals false. So we're going from low to high. So I'll just take the first 3, and then I will take the sum. So basically, we get the chromosome lengths here. We're using order function just to order them by the lengths. And I've set, I think by default, it's decreasing equals true. So it goes from highest to smallest, highest to lowest. Here I set false. Take the first 3, which will be the 3 smallest. So I just do sum. Very simple. How many unknown bases are there in chromosome 20? So to do this, we need to use alphabet frequency. And if we have run alphabet frequency on a DNA string, we will get the occurrence of the bases in that particular chromosome. So we need a chromosome. I said chromosome 20. So in this case, I'm working on HG38, so it'll be a little different here, but I can do $per20. There you go. And that's going to give me the sequence for chromosome 20. I can do alphabet frequency. And then it gives me a named vector of all the different frequencies. I got this many A's, that's C's, G's, T's. Because this is a named vector, I can index it by the name. So if I wanted to know, let's save it to an object. And if I wanted to know how many A's I have, I can just index by A. Here I want N. It's going to give me one called N, the value associated to it. Again, I'm working on HG38, so we might have slightly different numbers. Create a bar chart of the total number of ATCG bases on 20. So this particular example, we are going to use again and again and again. So let's actually run it. And we'll do a quick file, new R script. So this is Ggplot, right? So we're going to load Ggplot up. I'm plotting the base frequencies over chromosome 20. So I will, I'm going to have to do HG38. So then this will give me a vector of frequencies. I'm actually just interested in ACG, ATCG. So just as I earlier on subset by using N, I can actually use multiple values here, and I will just extract the alphabet frequency for the ones of interest, ATCG. Now, if I want to make a Ggplot, I need to create the data frame, because Ggplot's all about data frames. So I'm going to create a data frame with 2 columns, bases and frequency, and in bases I will put the names of the letters we're looking at, the characters are, bases we're looking at, so ATCG, I'll just put ATCG. And for frequency, I'll put the actual values themselves. So it'll be the actual numbers going on. Okay, so then I get my data frame. It's the bases here, the frequency here. That's suitable to go into Ggplot. And then I'm doing a bar plot. So we'll do Ggplot. I'll give it my data frame. I'll tell it my aesthetics, why I want to be frequency, Y up there. Going along the X will be bases. And then the fill, I also want to get it colored by different bases, just to make it look pretty. I'll do G on bar. Because I'm not asking it to calculate or sum up over anything, we do stat equals identity. So if I just run that bit, we'll get the actual base Ggplot. So G on bar, when you run stat equals identity, it's when you already know the frequency. And then I do theme minimal, just to make it look a little prettier. So it's not quite exactly the same, because I'm using HG38 rather than HG19, but it's pretty similar. Extract the sequence of chromosome whatever to whatever and retrieve the complement. I don't think that's too complex for them to run through. All I'm doing is using the $20, and then I'm doing standard indexing with square brackets as if this was just one long character vector. And I'm saying from that position to that position. To complement any sequence, you can just run complement as long as it's a BS genome object. Let me run that now. Oh, again, I still don't have HG. So we can do that. So this was my original sequence, and then if I get the complement, it's going to turn C's to G's, A's to T's, C's to G's, T's to A's. If I get, we can write that out to a FASTA file. So we just do, we have to turn it into a DNA string set. So I give it our DNA string here, pass that to the DNA string set object. And then again, I'm going to give it some names. Here, I'm going to just call it test FASTA. And then I can write that out to a file by providing my DNA string set. I give it the file path, and I tell it .file. Okay. look up the position of MYC in IGV, HD19, find the genomic coordinates. So I'm just going to have to follow along here because I'm not on HD19. But this is the position of MYC. Extract the sequence for the first exon. So in this case, all we need to do is get our genomic BS genome object, extract the chromosome we're interested in, chromosome 8. So I do $8, and then I'm going to index the position of that first exon. And that's what I would have looked up in IGV. The next thing then is to look for an ATG. So we can do count pattern ATG within that sequence. And then similarly after that, I'm going to ask you to look in GapDH. We'll do the same thing. We'll find the position. We'll do $chromosome 12. It's on chromosome 12. I'll do square brackets and an index to extract the start and end of the region I want to extract as a sequence. And then I'm just going to do count pattern and ATG. So I think the point here is, actually in HD19, I think still now, if you go look at MYC, which is a really famous gene, doesn't actually have an ATG, and an ATG is the start for translation. Right, so MYC famously has a non-canonical start site, start codon. And if you just look at most other genes, including GapDH, you'll find they have the very canonical ATG. So even though we don't know much yet about how we can interrogate data, we can go to IGV, we can get the first exon for MYC, and we can already discover it's a little non-canonical. It's doing something else to trigger a start codon. Okay, so that was the quick intro to sequence exercise. I'm just going to hop in now to the genomic ranges exercise. Genomic intervals exercises. We'll look at the solutions. Quite a bit to do. Okay. So first, install the actual two packages. We should know how to do that. We can load in the BioC Manager package, and then we can use the install from BioC Manager. I think this is just me being clever here. Ignore that. Read in the data mix CH12 with input CH12 peaks. This is a set of peak calls for the MYC transcription factor. So this is real data, which we're actually going to come across at ENCODE later. And create a G-ranges object, which includes the values of fold enrichment and -log10 p-value. Okay. So this is actually a very interesting file. So let's try and have a look at this. Let's have a look at it in the data directory. Oh, I'm in the wrong place. Hello. Let's go get it. University.github.io. So I'm just going to go download quickly this. May actually take a little bit of time. Control. Just give it a few seconds. What's going to be nice about this is that you can see here, I've set the comment jar. I've set this tab separated. What you can see here is data MYC CH12, whatever. The extension is .xls. So I have shown you that we can read in XLS files using, maybe this will take a little time, using the RIO package, RIO package. But in this case, and a lot of people do this, when they export their software, this says .xls, but it's just a tab separated file. And it's a trick that if you put .xls at the name of the end of your file, Excel will try and open it. It's a way of associating something with Excel. Now, just as we were talking about earlier on, if you name a file .far, it doesn't make it a more realistic, faster file. It's just a program to recognize it. Let's go in here, our course, data, we should have that MYC p call somewhere. XLS, let me try and open that with the TextPad or something. Maybe I can even just drag and drop it into R. I'm not sure. Oh, didn't like that. Okay. I can assure you it is just an XLS. It is just a text file, thinly disguised as an XLS. Did I get that? Okay. If we look at this file, we can also see some of the reasons we really want to take care of comments. So you can see here, all these lines are commented by having this hash at the beginning of them. And actually the real data starts post comments where we have chromosome 1, start, end, something which looks a lot more like a bed file or something we can turn into a G-ranges. A lot of programs are going to do this. But in this front bit, even though we're not reading it into R, you can see there are some really useful things, including the exact command we use to make that peak file, how we did it in that. So in this case, this is just a lesson to be able to read in a standard kind of peak file, posing as an XLS. It's just tab separated. We just need to make sure that we set the comment char to be hash, and we'll skip those first few lines. So then we can build the G ranges from this by giving it the chromosome column and make an I ranges with the start and end column. And then we can have some free mcols containing this score, fold enrichment, and minus log 10 p-value, just taking those directly from the columns in the file we read. Next thing is create a box plot. So I made this a G-ranges for Ggplot. This is a nice trick. We can just turn it into a data frame, as.data frame. And then with that, we can pass that to Ggplot. And now I'm going to use the seq names column to split along X. I'll use the Y, so up here, to give us the distribution of fold enrichments. And rather than fill up there, I'll use color equals seq names, and you can see I don't get the box filled with a color, I just get the outside filled my color of choice. Tell it plus G on box plot plus theme BW, and then we have a box plot like this showing the fold enrichment for peaks over all the chromosomes. Create a G-ranges object of the genomic intervals of chromosome 1 with scores greater than 10 and p-values less than 0.01. Export as a bed file. So all we need to do then is just use our standard indexing. We know that we can just extract intervals like rows here. So I'm going to take the column of fold enrichment and get a true-false vector for those greater than 10. I'm going to combine that logical with another one, which is going to be checking the minus log 10 p-values are less than this particular value here. And then I've coupled those together. I put them inside my square brackets for my G-ranges, and that means I just get the G-ranges back, which pass both these conditions. The fold enrichment was greater than 10, and the p-value, minus log 10 p-value was greater than this. To subset to chromosome 1, we don't actually need to do any overlap logic. We can just do another subset, and we can do seq names from the one we created here in chromosome 1. So we just check that the seq names are chromosome. With that, once we've filtered down to chromosome 1 peaks, which pass these filters, we can just use the rtrack layer packages function export.bed, give it the G-ranges, and then give it the name of the file we want to create. Reading a text file of gene positions containing config named as seq names column, genomic start and end from this file. So I've created a file of gene positions. This ignores the idea of having exons. It's just the start of the gene to the end of the gene. So we just want to read that in and export it again. So we can do IGV positions, read delim, read that text file. You can check out the text file to see how it is constructed. Is it comma, tab separated? It is tab here, so sep equals tab. From there, we just build the G-ranges. We put the seq names column as the chromosome names. We build an I ranges from the start and end columns. We can give it a strand column. We're then going to use the names function to assign names to our ranges, and they're going to be the gene ID. And then once we export that, we can do export.bed, give it the G ranges we've created, and then write that out to genes.bed. So someone raised a question in class here, which was a good one, is what happens if we just set names within here rather than assigning names afterwards? Actually, I'm not sure if we still got the solution up from when we were talking about it earlier. Let's look. Maybe not. Maybe in here. Oh, here we go. So the difference, oh, maybe it wasn't here. Okay. But we can just do it again very quickly. Do it very quickly. File, new file, our script. Let's make sure. Not in my history, maybe. Oh, it is. There we go. So if I try and build the G ranges like this and just set the names as if it was another column. This G ranges looks like this, and we have a metadata column called names. If I actually do names Tom and then give it a name that way, the names now, it's a bit narcissistic, I'm using my own name. So the name now is assigned here, and it's like a row name. Right? So actually that's what we can use to index our G ranges. When we export this now, and I can probably make this a bit more illustrative by putting share there. If I export this bed file now, it's not going to use the name up here where we set in the column. It will use the names we've set here. So let's try that. Bed. Bed. But we can even do it this way if we did earlier on. So if I build it like this, and I try and export that tom.bed, we can see we have no names. We have a dot for the score column and a dot for the names. If I went back and I assigned names Tom, export bed, tom.bed, we should now actually get a name put here. Okay. So we need to set names explicitly using that names function. Created G ranges of the transcriptional start site for every gene. Great. All we need to do there is resize our gene positions with a width of 1. We just want exactly the transcriptional start site, and we'll fix the stuff. Extend these G ranges to be plus or minus 500 base pairs around transcriptional start sites. So now we have built our TSS positions by taking the gene positions, looking just at the start of them, and fixing the width to be 1. So that'll be perfectly the TSS. We can now expand around them by passing that new object to the resize function, saying width is 1,000, but fix on the center. And that means it's going to take that value and expand around it. If it was the center, and give us 1,000 base pairs, 500 base pairs each side. Total width of 1,000. Probably going to have to skip that last question because I've got a meeting coming up. But we can do this next one's here. Create a bed file called filtered mic on tss.bed of our mic peaks from question 4. Oh, great, this is useful, which overlap G ranges of plus or minus 500 base pairs around transcriptional starts. So I've already created my G ranges for these mic peaks up here. We exported them, but we're going to use those in memory. So if I just take them and then I subset them using our logical indexing with over, I find the regions, the mic peaks which overlap our newly created TSS regions. And then I can use that with square brackets to index my peaks. And then that will be a new G ranges just of those which overlap the TSS positions we've created. And I can export that to bed. Use that. Okay. Import the summits.bed file into granges. The 5th column in the file represents summits height. So in this case, I'm just going to import this bed file from our data directory. And it's actually nice when you run Max, it gives you a bed file as well as that XLS. And then we just need to create a density plot of summits overlapping and not overlapping our TSS pipeline. Okay. So in this case, we're going to try and add to our G-ranges a new column called overlap. We can do that just like with a data frame. We do my summits $overlap. I'm going to take a logical of my summits which overlap the TSS positions. This is going to give me a big true false for every summit which overlaps the TSS will be true, false. And then I'll use the if else. And the if else will turn this vector of true or false. When it's true, it will return TSS, and when it's false, it will return not TSS. So I can basically turn my true or false into a character vector here of TSS when it's true, not TSS. Then, once I have this summits, I need to turn my G-ranges into a data frame so I can use it with Ggplot. And then I'll have my data frame here, pass to Ggplot. I want X to be the score, so that came from the bed file. I want fill to be the overlap, and that's what I created here, just to say whether or not we overlap for the TSS or not. And then I'm going to do geom density to make a density plot. I'm going to set alpha so that we can kind of see a little bit underneath the plots. So alpha being opacity, transparency. And then I need to facet wrap, so I'm going to split it then by the seq names, the chromosome names, and that's why we've got one across here. And I'll add a theme BW just to make it look a little bit prettier. Okay, I think I'm going to have to call it a day here. I will run through these other exercises if anyone really requests. I just got to make a quick dash to my next meeting. If you have any questions on G-ranges, please let me know. Reach out by the help or email me directly. Do remember, we're going to be running through the same kind of exercises over and over again. So we're going to drill this in as we expand and start to do. Have a great weekend, and I will see everyone next week, Friday.